Hello, my name is Chen. In this video, I will talk about polynomial-time trace reconstruction in the low deletion rate regime. This is joint work with Chen, Anindya, Rocco, Servedio, and Sandip Sinha. So first, let me tell you what is the trace reconstruction problem. In this problem, we have an n-bit string x, and we pass x through the deletion channel. This channel deletes each bit of x independently with some probability delta. So in this example here, the channel deletes the second bit and the fifth bit. Then the channel outputs the concatenation of the surviving bits. So here it outputs 11101. To give you another example, the channel may delete the first bit and the second last bit here, and then outputs 01111 this time. Just to give you one more example, here this time only the third bit is deleted, so you get a longer output this time. Okay. So note that the deleted positions in X are not revealed in the output, and also the length of each sample is not necessarily the same. So these independent samples coming from the deletion channel are called the traces of X. So here is the trace reconstruction problem. We are given traces of an unknown n-bit string X, and our goal is to reconstruct X exactly with high probability. Note that X is not allowed to be encoded before passing it to the deletion channel. So the basic question is to understand how many traces suffice to reconstruct X, and whether there is an efficient algorithm for this task. So this problem has some applications in computational biology. For example, you can think of traces correspond to the mutated DNA sequences. And then the reconstruction problem will be to reconstruct the original DNA sequence from this mutated sequence. So here are some previous results on this problem. So the problem was actually first introduced by this work by Batu, Cannon, Kana, and McGregor in 2004. And in this work, they gave an efficient algorithm that works for any deletion rate that's less than 1/√n. Later, Adorno, Servedio, and Nazarov and Perez independently gave an algorithm for any deletion rate that's bounded away from 1. And the algorithm uses exponential to n to the 1/3 samples. And very recently, Chase managed to improve this exponent 1/3 to 1/5. In terms of lower bound, in this other work by Chase, that built on the work of Holden and Lyons, he showed that for any constant delta, the trace reconstruction problem requires n to the 3/2 traces. So as you can see, the recent works have been focusing on improving the sampling complexity and for constant deletion rate. And you can see that the algorithms are not as efficient as the one given by BKKM here. Also, the lower bounds given don't seem to hold for subconstant deletion rate. So in this work, we asked the following question. Suppose we insist on the algorithm being efficient, then what is the largest deletion rate that we can handle? And this is our result. So we show that for any constant epsilon and deletion rate delta that is less than 1/n to the 1/3 plus epsilon, then there is an efficient algorithm that recovers X with high probability using polynomial number of traces and time. Okay. So our algorithm is very similar to BKKM, which is also alignment based. and it improves from improves on this work because our work handles a larger deletion rate. So we actually improve the deletion rate from n to the 1 over square root of n to 1 over n to the 1/3. So while this improvement may seem not much, note that when delta is roughly 1 over square root of n, then already the previous upper bound uses exponential to the n to the 1/6 traces. And we believe this alignment-based approach given by us and BKKM could potentially work for larger deletion rates. So let me now give you the algorithm overview. And before that, I need to introduce a notion called testers. These are just some non-subwords in X that is of some repeated constant size pattern. So just to give you an example, for example, if X is this string, then here is a 1 desert because it consists of some consecutive sequence of ones, which is of length at least 1 over delta. And then here we have a 0, 1 desert because these are just 0, 1, 0, 1, 0, 1, 0, 1, and we have at least 1 over delta many of them. So our algorithm alternates between the following two procedures. The first one is called bitwise majority alignment. In short, it's called BMA. So we construct X up to a desert. And then the next procedure is called find end. And it tries to locate and align some new traces to the end of the desert. So here is a simulation on an example. So this gray X is our unknown X. At first, we draw some fresh traces, and then we run BMA on these traces. Then BMA will return a candidate output X hat. So X hat may not agree with X, but what we know for certain is that it's going to agree with X up to the first M piece of the first desert. So now we know there's a desert in X. Then we switch to find end, and find end will tell us the endpoint of this desert, which is here. It will also try to align the traces, but that it will, it locates the position where the endpoint of the desert appears in each trace. So once we know the endpoint of a desert in X, then we can fill out this piece because we know the pattern of the desert when we ran BMA. So now we switch back to running BMA, and then it will continue running BMA on these new traces, and then it will reconstruct X up to the second desert in the X. Again, we know that it's correct up to the first M piece of this second desert. And now we switch to find end and find the end location of this desert and locate this endpoint in some new traces. So once we have located this endpoint, we can switch to BMA and continue reconstructing X. And because now there's no desert in the end in the string, so we can finish running the algorithm. So let me now say more about the BMA algorithm. So this algorithm was introduced by the work of Batu et al. So it takes some not n traces as input, and then what it does is it outputs a candidate X hat of X. So in this work, we prove the following guarantee. First, of course, BMA runs efficiently. And second is that we show that if at the beginning, most of the traces are aligned correctly, then with high probability, the candidate X hat is correct up to the first m bits of the first desert in X. So as you can see, the algorithm is very robust, and this robustness comes from majority in the algorithm. Okay, so let me now explain how the algorithm works. So at the beginning, the algorithm would set up some pointers for each trace, and each pointer points at the beginning of each trace. Then we will recover X bit by bit. For the first bit, it will take the majority of the pointed locations in the trace. So here we have the majority is 0, so it will output a 0. And then it will update the pointers as follows. If the pointer output gives us the correct answer, then we will move the pointer forward by 1. And if it doesn't, then it stays still. So the intuition is that if the pointers agree with the output, then we think of this trace as being aligned correctly. So we just move the pointer forward. Otherwise, we think of it as misaligned, and then it will stay still just to try to correct this misalignment. So let me simulate a few more steps of the algorithm. So now we try to recover the second bit, and this time all the traces are pointing to 1, so we output 1, and then we update all the pointers by moving them forward by 1. And in the next step, this time the majority is 1, because 3 of them are pointing to 1, so we output to 1, and then we update the pointers as before. And then we just keep running this algorithm using the same principle. Okay. So let me talk about the analysis of the algorithm. So in the old analysis by BKKM, they show that if the deletion rate delta is at most 1/√n, and also if X has no 1 deserts or 0 deserts, these are just a long sequence of consecutive 1s or 0s, then BMA actually outputs X correctly with high probability. So in their analysis, they rely on the fact that no 2 consecutive bits in X are deleted. And that's why it only works when delta is less than 1/√n. It's not hard to see that actually BMA does not work or will not work when there are 1 desert and 0 deserts. Just consider the O1 string. Each time the pointer of each trace is going to move forward each time. But after running about 1/delta many steps, then each trace is going to miss some bits because of deletion. So the algorithm would never output the correct number of 1s as the input, as the unknown input. So in this work, we give a new analysis of the BMA algorithm. We show that when the deletion rate is at most, say 1/n to the epsilon, and if X has no S deserts for any constant size S, then the algorithm outputs X correctly with high probability. So here we are making a stronger assumption than the one made in BKKM. And that's why when we deal with the desert, when we try to locate the end of the desert, we have to do more work. So to help our analysis, we have the following visualization of the trace Y. The way we think of it is as follows. So for trace Y, we first write down X, and then we cross out the deleted bits in Y. And we have 2 pointers. One, the left pointer is pointing to the bit that we are trying to recover, and then the right pointer is pointing to the location pointed by the pointer in the algorithm. So here we introduce a distance, a notion called distance, which measures the amount of misalignment at time t. And this is basically just the distance between the current pointer in the trace and the bit that we are trying to recover. So in this example, the distance is 3. And in our analysis, we show the following invariant. So we show that if X has no deserts, then we have high probability at each step of the algorithm, the distance of each trace is actually non-negative. And also the sum of the distance of all traces is at most the number of traces divided by 10. So from this, it's not hard to see that most of the traces are aligned. Okay, that was all I wanted to say about BMA. So now we move to the analysis, the algorithm of find end. So the find end algorithm takes a few things as input. First, it takes a reconstructed prefix of x hat. Then it also draws some new traces, not n of them. And it also has access to the deletion channel. Because during the execution of the algorithm, it's going to draw some additional traces. And this find end algorithm is going to output two things. One is the candidate endpoint of the desert in X, and it also tries to align these new traces. So it will output some candidate locations of where X and the endpoint of the desert appears in each of the traces. So the guarantee given by the algorithm is that find end uses polynomial many traces, and it's going to give you the correct endpoint, and most of the pointers are going to align correctly. So the find end algorithm is actually a bit delicate, so I will only give you a rough idea of how it works. So as a first step, the algorithm will try to find an interval so that most of the traces is going to contain this endpoint in this interval. So this interval is of length sigma, which is about square root of delta n log n. And this looks that this length is basically how far the point xn can deviate from its expected location in a random trace. So in other words, you can think of this as giving a cost estimate of the expected location of xn. So once we have this interval, then we try to use we try to find a signature subword called sig in the unknown x that contains the endpoint of the desert. Okay. So the definition of signature is a bit delicate, but essentially we want signature to be very different from the pattern in the desert, because in the next step we try to use this to locate the endpoint in the new traces. But of course, this is not always possible, because sometimes this endpoint may get deleted in a trace. And if this happens, then we have to output something like an error or something. So now we can use 3 to align the pointers in the new traces. And we can also run 3 on polynomially many traces to do and then do an empirical estimate of the expected location of the trace. So here we have to be a bit careful in the algorithm because of the fact that 3 is sometimes going to reject when it cannot locate the endpoint. So we have to do some scaling when we do the empirical estimation. So here I want to mention that each of these 3 steps relies on the fact that sigma is much less than 1 over delta. And the reason is that we want to ensure in most traces, there's no deletion in the interval J, or in more generally, we don't want any deletion in interval of this width. And this is the reason why we require the analysis. So this is the reason why it only works when delta is at most 1 over n to 1/3. So that's all I wanted to say about finite. And here is a summary of our result. We show that for any constant epsilon and deletion rate 1 over n to the 1/3 plus epsilon, there's an algorithm that we call first X efficiency. That means using polynomial many traces and time. And at the high level, our algorithm alternates between 2 procedures. The first one is the bitwise majority alignment, which correctly we construct X up to the first desert in X. And then we use the next procedure, finite, to locate the endpoint of the desert. And also we locate where this endpoint appears in each of the first traces. And as mentioned before, this analysis for finite requires this square root of n delta to be much less than 1 over delta. And this is the reason why our algorithm only works when delta is less than 1 over n to the 1/3. So obvious open problem is that whether we can overcome this barrier. So we would like an algorithm, an efficient algorithm that works for example, say delta equals to 1 over n to the 0.32, or more generally, we were hoping whether we can achieve delta to be any polynomial. So this is all I wanted to say about this work. Thank you for listening.